So thanks, Christophe. So I will talk about the first stars and the dark matter. So my outline is firstly I will review the progress on the formation for first stars in standard cold dark matter model. Then I will talk about the first star formation in warm dark matter. So for the warm dark matter, it's less popular. Okay. So here shows a picture for our universe as a function for time. So here the Big Bang. So in the 1 million years, after 1 million years, that's the simple radiation. After simple radiation, elements begin. So that's a recombination error. So in this time, we cannot see anything. So we call it a dark age. So after first star formation, the dark age is finished. Okay, eventually it will evolve. It will form a very complicated structure as we see today. So what's the first stars? So we also call it first generation of stars and the poppy 3 stars and primordial stars. So we call it primordial stars because they were formed out of primordial gas. That means in the environment there are any metals and dust. So the star formation in this environment are very different. So when we care the first stars and its initial mass function so much, the reason is the first stars they produce the first light to realize our universe, and also generate heavy elements required for the subsequent normal star formation and galaxy assembly. So initial mass function is also important because the metal production is very sensitive to the initial mass function. So for example, if first stars are within this mass range, so they will end up as type 1 supernova and left over neutral stars. In this case, they will eject some metals. But if they are in this mass range, 25 to 40 solar masses, so they will end up as type 2 supernova and left over a black hole. So there are also some metals in this case. But if they are in 40 to 140 solar masses, they will collapse into black hole directly. So in this case, there are no any metals. But if in this mass range, they will have a huge explosion. But if the mass is beyond 260 solar masses, they will collapse into a massive black hole directly. So in this case, there are also no metals. So that's why we care initial mass function for stars very much. So that's from Worsley et al. Result. So there are some outstanding questions on the first stars. So firstly, we want to know how was the first star formed. Also, we want to know when did the first star form, and also where was the first star formed, and what's the initial mass function for first stars. So what are needed to make the first stars? So firstly, we needed the assembly for dark matter structures to provide the potential well to constrain gas. So if dark matter is cold, so the structure to form first stars is dark matter halo. So if it's warm dark matter, the first star can be formed in dark matter halo, also in filaments, as well as pancakes. So that's a gravity process. So also we need some gas physics. So we need a gas to collapse to very high density to make a protostar states, the density needed to be 10 to 22 cc. Okay. So what we have now? So if gas temperature is less than 10,000 Kelvin, so only molecular hydrogen is the main coolant to enable gas cooling. So in this case, we need a formation for molecular hydrogen. There are 3 channels to form molecular hydrogen. There are 3 processes. So the second process is the dominant one. For the 3-body reaction, they only dominate at a very high density. That's 10 to 8 cc. So what did the numerical simulations tell us? So there are currently 2 kinds of simulations to do first star formation. So firstly, the AMR simulation. That's it's done by Tamabir et al. In 1998. So in Tamabir et al. Simulate one object with standard CDM cosmology. And Ocean Norman, they simulate 12 objects with lambda CDM in 2006. So in second approach, that's SPH simulation. The Fock-Brown did the first one. But their simulation are start from not realistic initial conditions. It's not a cosmological initial conditions. Yoshida et al. Did one object with lambda CDM. So I did 8 objects, also assume lambda CDM. So the agreement is no fragmentations occur below mass scale thousands solar masses. This mass scale is roughly the Jeans mass of a primordial cloud due to molecular hydrogen cooling. However, the difference in details are significant.
Is that a function of redshift? Is that a function of redshift?
Yeah. So, for example, Ocean Norman, they did from redshift 30 to 15. I did from 15 to 50 to 15. So actually, we cover a very large redshift range. But difference is not due to redshift. So when people see first star mass is more than 100 solar masses, in arbitrary simulation, 80 solar masses gas cloud. It's in Jeans and stable. Also, nobody found fragmentations in simulations. The third is the gas accretion onto the central is extremely high compared to star formation today. This can be roughly understood by Frank Schultz's self-similarity solution model. That's gas accretion rate is proportional to sun speed cube. So for star formation today, the gas temperature is 5 Kelvin. But for first star formation, because the molecular hydrogen can only cool gas to 100 Kelvin. So you can see much difference in this sun speed. So this will introduce very different gas accretion rate. So people see first star probably is more than 100 solar masses. But the exact mass is not predictable because of the poor understanding of accretion physics and feedback. The conclusion on first star in CDM is if dark matter halo is more than 10 to 5 solar masses, they can compress enough primordial gas to achieve significant Bayesian core density and temperatures. So H2 formation proceeds and cools core Bayesian to 200 Kelvin, and to 10 to 4 cc. So at this density, local temperature, local thermal equilibrium is reached. Then gas cooling become independent on density. So the collapse will be very slow until density reach 10 to 8, so 10 to 8 cc. So at this density, three-body reaction to form molecular hydrogen will become efficient. So because of the formation of molecular hydrogen, the collapse will speed again. So finally, the collapsing core doesn't fragment, but form a single massive stars. Okay. So what's the initial mass function for stars? So very likely to be very massive. So we see that's more than 100 solar masses, but with much uncertainties. The reason is firstly we don't know how angular momentum transport, are transport. Okay. So there can be some due to some dynamical reason. For example, if in the center, if a bar can be formed in the center, the bar can transport the angular momentum. But if in the center there are a disk, so the only mechanism to transport the angular momentum is viscosity. Secondly, we don't understand the accretion physics. Also feedback. Feedback is also a problem. So whether or not there is a magnetic field, we also don't know. Also, somebody argued dark matter annihilation can hit the gas to prevent the gas collapsing. So in conclusion, there are much uncertainties in the initial mass function for first stars. So here I will talk about the first star formation if dark matter is warm. So in the warm dark matter, the properties of first stars are very different. Okay, so they're different in a number of ways. So firstly, in the location they are very different. Also the formation path. The possibly initial mass function can be also very different. So why we want to do first star formation in warm dark matter model? The first reason is the small scale power spectrum of universe is poorly constrained. So why not? Secondly, it's harder to explain central cusp of Delphi galaxies with CDM model. The third reason is we don't have a convincing model to explain the abundance of satellites in our galaxies. The fourth reason is the warm dark model is as good as CDM to explain large scale distribution for galaxies. So here I show power spectrum of our universe. So on very large scales, they are constrained by CMB, also by cluster abundance. But on the medium scales, they are constrained by galaxies clustering, like SDSS and 2DF. So actually, we don't know the power spectrum at very small scales. They can only be constrained by lambda alpha first. But there are much uncertainties in constraint on power spectrum on such scale with lambda alpha. So here is the theoretical curve for comparison for power spectrum in CDM and warm dark matter. So for CDM, the slope, there are always power on all scales to infinity small scales. But for warm dark matter, you can see there are very sharp cutoff at at a power spectrum. So actually, no any fluctuation below these scales.
What's the mass of the one particle?
Here is probably for 3 keV gravitino.
Isn't that ruled out already, though? I mean, like mass?
No, probably not.
What is your mass?
Here is the 3 keV gravitino.
For very special model.
Sorry?
This is for very special supergravity model.
Sorry, I didn't get it.
Textbook gravitino mass is 100 GeV.
Yeah. So here the gravitino. It's not a CDM. It's gravitino mass.
But it's very special model for.
Yeah, it's true. But also there are some model for stellar neutrino. So for stellar neutrino, probably this mass is for such free streaming lines. The corresponding mass scale is 10 keV probably. 10 keV for stellar neutrino.
The mass doesn't really matter. All that matters is the
Free, yeah, that's a free streaming mass scale. Okay. Yeah, depends on nature of document.
It's function of the temperature of the particle, not the mass, right?
as long as whatever particle you're talking about, as long as it has this power spectrum, the results will be pretty much the same.
Yeah.
Independent of the mass of the plate.
CDM is very bad. LDM is not very much good.
Oh, well, that's a different argument.
Yeah, this is different.
So here the plot from Bimmer. They did some simulations on comparison for largest structure of universe. If assuming different kind of document particles. For the up plot, that's for cold document model. So you can see lots of structures, substructures. Okay, so in the middle panel, that's for warm documenter. So you see there are less substructure when compared to the CDM. So in the lower panel, that's for hot document model. You can see there are no substructures because no power fluctuation in the initial conditions for small scales. So actually, no structure can form below some mass scale. So you can see lots of difference in if document is different. So we did the simulations by identify a cluster supercluster region. Okay, we did some zoom simulations and assume different nature of document. So at early time, you can see if the document is cold, you can see lots of substructures. So you can also see some filaments, but the filaments are broken because they are always power spectral. They are always power on all scales. But for the warm document model, you can see very different. You can also find the filament, but the filaments are very small. The reason is no any power on small scales. So there are no substructure in the filaments. So here we can see more clearly. So in this case, we assume warm document is 3 keV gravitino. So the free streaming mass scale is 3 times 10 to 8 solar masses. So the smallest halo should have compared mass as 3 times 10 to 6 solar masses. So here is the movie to show the evolution for our high resolution UGF simulation. So you can see firstly there are some pancakes formed. In the structure formation is first collapse into a pancake. Then pancake collapse along another axis to form a filament. So that's the first structure in the if document is warm. Okay. So you see the very dense filament. So here show the map for the structure of this filament. That's for the gas. Okay. So here show the temperature map. The red panel shows the density map. So the temperature, for the yellow, for the bright color, that's corresponding to high temperature. But for the dark color, that's corresponding to the low temperature. So you see in the around the filament here that's the high temperature. So the gas is shock heated. The high temperature is due to the shock heating when the gas collapses. But in the center of filament, you can see that's very dark. That's because molecular hydrogen formation and associated cooling. So the gas first heated, then form molecular hydrogen. The molecular hydrogen will cool the gas and make a gas to collapse into very high density. So the density map is the bright one, is the high density. You can see that's very dense and very uniform. So that's very different from CDM. In CDM, that's the one simulation I did for the CDM. So here's the first structure for CDM. You can see in the central region that's pretty round. You can also see the filament, but the filament is broken and also some substructures. That's for document. But for the gas, you can see in the central region that gets it form two clumps. So they are pretty round. So when compared to this plot.
So now basically these are the first objects that form your simulation in hot dark matter and cold dark matter, right?
Yeah.
So it means the structural formation is actually slower in warm dark matter scenarios. And what is the same? It's the same in the central density. Why do you compare them with these two redshifts there, 23 and?
It's not a redshift 0. So that's for.
Why do you compare?
So I mean the morphology. I'm comparing their morphology. Their morphology are very different. That's but they all are first structures.
But do the central densities in each object actually agree?
For the gas density, they are very similar.
Okay.
For the gas density in the center, they are very similar. So I'm compare the phase. I'm compare as the phase. They can form stars. But in the warm dark matter model, because the first structure form late, okay. So the first star will form slightly late.
And this is the densest part of your simulation in the filaments. So your halos that also form even later in this warm dark matter.
Yeah, actually in this phase, no halo formed. The halo is not formed yet.
Okay.
Eventually, you can imagine they will collapse along the longest axis. They will eventually collapse into a halo, but at this stage, no halo yet.
Now is the constraint realization or?
Sorry?
How did you, what was the box size, I guess, then?
The box for this one, that's probably 500 megaparticle. We did a zoom-in simulation. It's a resimulation.
But you would expect it to collapse almost spherically because it's so rare,
I'm just surprised that it's talking to a filament as opposed to a halo, because it's the first object that formed in that volume.
Yeah.
I mean, that's just very surprising.
But actually, you can see this plot. You can see there are many filaments. This plot is this is structure at a little time. Okay, you still can see many filaments. So the filament is generic for the warm dark matter model, right? So eventually, actually this object is the so the filament. So the first filament will eventually collapse into this object.
It's also redshift 15.
That's the progenitor for this 15. But for the plot I showed before, that's for 20. That's for 25 probably. Yeah, that's for 2023. So the filament is the progenitor for this central object.
So what's sigma on this mass scale? Like for this redshift?
For this one, I think so for M star probably that's M star is 1 solar masses.
No, but I mean sigma.
Yeah, sigma probably is 7 sigma, 7 or 10. 7.
You mean sigma 8?
Sigma,
No,
7.
I mean sigma for this sort of mass scale.
7 probably. 7. 7. You think so? Okay. So here you can see structure for filament more clearly. So here I did for so here I make a plot for the structure of halos in different projections. Okay. You can temperature map and the density map, different projections. So you can see filament is pretty uniform. Okay. So here is the transformation of the filament to make the long axis parallel to the to be parallel. So here's the gas temperature, here's the density. So it's pretty uniform. The vector show the gas velocities. So you can see the gas accretions. It's so you can see gas collapse into filament directly. So it's very different from the CDM. So the accretion is very similar to be spherical, but here it's very different. It's cylindrical.
Dark matter.
No, it's a gas.
It's a gas.
Yeah.
Use a gadget?
Yeah. So here is a piece of filament. That's the so that's the long axis. That's the short axis. So the wet point are dark matter. So the cyan point are for the gas. So you can see you can see here the dark matter do orbital crossing. They do oscillation along here. You can see in the central filament they are baryon dominant. Gas reach very high density. So you can see it more clearly. Show the gas density for each particles as a function for radius, as a function for distance from the central filament. You can see at the very inner filament, gas reach very high density. That's 10 to 5 centimeter cube per centimeter cube. So, so here show the temperature, gas temperature, as a function of distance of gas to the filament. So at the central filament, gas has very low temperature because of the molecular hydrogen.
So you stop at 200 K, or do you follow, at which temperature do you stop your calculation?
From redshift.
Temperature, do you temperature floor in your simulation?
Yeah. Temperature flow is that's probably 100 Kelvin.
Say again?
100 Kelvin.
100 Kelvin.
Yeah, that's the limitation for H2 cooling.
Oh, but your adiabatic expansion makes the gas mean temperature of like 5 Kelvin. So the gas before it shocks should be about 5 Kelvin.
Yeah. So, because it's only because scale.
How can you have a flow of 100 Kelvin if you know the gas is in reality 5 Kelvin?
I mean 100 Kelvin. That means for the central region because you always have a gas collapse. Okay, you have a gas collapse. You always have adiabatic heating. So the gas in the central region in the center cannot be lower than 100 Kelvin because you don't have cooling mechanism to cool the gas.
In this Pavlovich pancake has zero entropy gas in the center and it goes up as you go out because the first collapse occurs at zero entropy. You get a power law going in from the initial, if you don't have cooling or heating. Now, unless you take some heat from the CMB, it'll be, it should be a power law going down to about, a few Kelvin in the center. And
But problem is gas keep because gas keep collapse. Okay. So, but you don't have a mechanism to cool gas below the 100 Kelvin. So gas is always gas temperature is always above 100 Kelvin. But in the outer region, you can see here. So you can see here actually when gas is very far away from filament, you can see gas has a very low temperature compared to the center. Okay. So what's the fate of this filament? We know there are no any power in this scale. So initially, actually, if there are no no any perturbation on this scale. So if gas keep collapsing, the gas will collapse into very high density to form a single stars in the filament itself. So the star formation will happen in this very long filament. So here we have to use some linear analysis to predict the fate of this filament. So in the linear theory, a filament is unstable to access symmetrical perturbations of wavelength greater than 2 times filament diameter. When this lemmas of filament is 2 times sound speed square. So if mass of filament is larger than this value, the filament is unstable. Okay. So when the line mass of filament exceeds the value for this equilibrium, the perturbation will not be able to grow much. The entire filament will collapse toward the axis as long as equation state remain isothermal. So this is from classical theory. So that's some plot from some Japanese group. So they did some simulations on the two-dimensional collapse filament. So if gas is isothermal, so the gas will always collapse into the filament, no any fermentations. So the fermentation can only happen when gas equation of state is not isothermal. So if it's not isothermal, you can see there are some fermentations. So of course the fermentation can so these clumps can also merge to form the big lumps.
What does non-isothermal mean? Is it like gamma 5 thirds, or what do you mean by non-isothermal?
Isothermal, that's equation of state.
Well, there's an infinite number of non-isothermal equations of state, so non-isothermal, you still have to say what it is, right? Otherwise, you cannot take it.
So the gamma is if gamma is not 1.
Yeah, I understand it's not 1, but
Okay.
it has a value, right?
Yeah.
Value is 5 thirds, is it 100, what is it?
Any, probably only so any value gamma, any value larger than 1, the filament will break up. Can be in any value because filament is very unstable. They have very dense in the central range. They are very dense. They are very unstable. If gamma is not 1, they will break up. So you don't think so?
No, because the gene stability only depends on linearly on gamma, so even an isothermal gas is gravitationally unstable above the gene's mass. And increasing gamma usually makes it more stable because the gas is more stiff.
Yeah.
Typically, if you take water, for example, it becomes incompressible with a large gamma.
But problem is this is G's mass is not relevant here. This is a different collapse. It's a filamentary collapse. It's not a spherical collapse. So G's mass is not relevant here. That's two different collapsing process. So for the instability of this filament is it's only relevant thing is its mass. It's Lang mass. It's a Lang mass for filament. G's mass is not relevant.
Well, it's the same things, though, right? I mean, the state, which means the gas, has fewer internal degrees of freedom. That's what gamma measures. So how can it be that a gas which is stiff collapses more easily?
The problem is the problem is there are two time scales. So one time scale is perturbation for the growth of perturbation. Another time scale is the dynamical time. That's for the gas collapse. If the perturbation grows more faster than dynamical time, the gas will break up. Otherwise, it will not break up. So that's different from the G's mass argument. Okay. For the fermentation, there are two possibilities density scale for this filament. The filament can be non-isothermal. There are two density scales. So the first scale is the density 10 to 4. So at this density, local thermal equilibrium level population are achieved. So the gas collapse will be slower. So at this density, the fermentation mass is 100 solar masses. Okay, that's from some ideal simulations. So another density scale is the 10 to 12. So at this density, gas become optical to the H2 lines. So at this density scale, fermentation mass scale is 1 or 2 solar masses.
Yeah, what you're saying it's a gas, you mean optically thick.
Yeah.
And you're saying when you become optically thick, you form small fragments. Wouldn't you expect the opposite? If you're optically thin, you can cool locally and cooling can run away. If you're optically thick, you become an ideal gas. And ideal gas and the well-defined Gibbs mass will be low.
No, Gibbs mass is not relevant here. It's not due to Gibbs mass. That's only due to.
It's a two-dimensional equivalent.
No. That's different. That's equilibrium mass. Only equilibrium mass is that's relevant. Gibbs mass is not very relevant. If the mass is bigger than the equilibrium mass, the filament will break up. Otherwise, it will continue collapse.
But you're talking about optical depth here.
Yeah, optical. So because the gas become optical, so the gas cannot. So gas collapse will become slower because the gas. Because the gas cannot radiate the heat. Gas is heated up by the H2 radiation. Because the gas cannot cool as fast as before. Okay. So in this case, gas collapse will. So the gas collapse will become much slower. The perturbation will grow more faster than gas collapse. So the filament will break up. So the key idea is the competition between the growth between growth of perturbation and the gas collapse. If perturbation grows more faster than collapse, the filament would not break up. Otherwise, the filament will break up. So here we have to remember the filament is very uniform on large scales. Okay, so if without any power, the gas will always continue collapse. So now we should ask where are power? So where are power on small scale from in warm document from? To trigger the some gravitational to trigger the instability. So because it's very uniform, okay. So we have to look for some seed to trigger the instability. So here we assume the gravity will do this task because you can see there are some edge effect. Also, they are not in perfect symmetrical. Okay. So we think this transfer power from large scale to small scale is very slow. So we don't think the filament will break up at 10 to 4 density at 10 to 4 cc. Okay. So in this case, the gas will very likely to break up at a second density scale. That's 10 to 12. So that means the range of mass of stars will be formed in a very huge burst. So because the filament will form, fragments will have a range of masses. So some fragments have large masses, but some fragments have small masses. So they will form a range of mass of stars. So the summary is, so in CDM, the first star form in a spherical collapse, okay? But in CDM, they form in the filament. And in CDM, they only form a single massive stars. But in warm dark matter model, they will form many stars in a burst.
So is that a statement based on a simulation, or you get an analytic calculation of that instability? Because as I say, I don't see why a high optical depth should lead to small scale fragmentation. If anything, I would have expected the other way around, because I can start with pressure. Is that based on somebody's else's calculation, your own simulation, and n-body simulation?
From some our argument are from some ideal simulations by a Japanese group.
So you are using a optical depth as an equivalence to the equation of state.
Yeah.
That's what you're assuming.
Yeah.
But again, so you're saying a higher optical depth corresponds to a larger gamma. That's what you like to argue, and therefore corresponds to fragmentation. That's the logic.
Yeah. Yeah. No, high gamma, that's, I think high gamma, oh, sorry. High gamma corresponds to high optical depth. Okay? So gamma, if gamma is 1, that's isothermal. Okay? So here's the conclusion. So in CDM, that's so the first stars are massive, and the short-lived stars because they are massive. For warm dark matter model, because they have both low and high mass stars. So if dark matter is warm, so we should observe some low mass stars today. So actually, in recent years, we found two very low metallicity stars in our Milky Way. So actually, this agrees warm dark matter model better. So also actually, you can think, because the filament is very long, and also this filament is very massive, that's 10 to 7 solar masses. So if they form many stars in the filament, and also the filament will eventually collapse into this along this exercise. So you can imagine there are many collisions in these stars. So sorry. So actually you will think eventually it's very easy to make a massive black holes, massive black holes. Also, there are some implications. So for warm dark matter, so we are assuming a very, very heavy warm dark matter model. If warm dark matter particle mass is smaller, so you will think the free streaming scale is bigger. So the first filament can have much high temperature than our case. Our case is at 10 to 4 Kelvin. So if the filament temperature is even higher, so you will think the dwarf galaxy will likely form with fermentation of filaments. So what are properties for dwarf galaxies if dark matter is warm? So it's not clear.
But isn't this constrained by current planar forests? So you choose your mass that is just consistent with the current limits. That was my impression.
So actually, I'm seeing the concentration from lambda alpha. There are some uncertainties. So actually, 3 keV is not very big. Actually, it's not very low actually. So in previous constraint, that's for probably for 1 keV warm dark matter mass. In my case, that's 3 keV. But if that's 2 keV, you will think the filament can form dwarf galaxies. In 2 keV, temperature is much higher than our case. other applications is there are, so one is the many constraints on warm document particles should be reversed. For example, renunciation. So before people think only halo can form stars. So they use renunciation to constrain warm document particle mass. So, but actually in warm document model, you will think many stars can form in the filament. So this constraint should be reversed. So also for lemma alpha first. So you will think the feedback from the filament, because star formation, they will generate winds to change the small scale power spectrum. Okay. I stop here. Thanks.